So good morning, all of you.
Good morning, sir.
Good morning, sir.
Um, so in the last class, we have gone through the deletion of the binary search tree node. So I hope we have discussed a lot about that, and I also imagine that you have done a little bit of code. So how many of you have done it? How many of you have tried it? Just raise your hand. Let me see. Tried deleting it. Nobody? Nobody tried deleting a node? Okay. Saurat, Srinidhi, Mokshagna, Shreya have tried it. Mohit also tried. Very few people. Only 5. There is nothing lost in trying, right? You can try out, and if you don't get, then I did not say that you are successful or not. I said whether you have tried it or not. So trying is also a very difficult task for us, I think so. Okay. Anyway, I will also keep a discussion. So in this week, I think we need to take some extra classes if possible. So when is the free time tomorrow on Thursday for you?
So from 11 to 2.
Okay. Then we will take from 1 to 2. Then I have 2 to 3 class. I will take 1 to 2 a small session for you. So not like the previous thing, like you need to attend on Friday. On Friday, which periods are free for you?
3 to 4, sir.
3 to 4. Let me check out that on Friday if I have any class in between that one. Okay. No, I have a class at 3 to 4. So remaining, I think you are not free at all. You are only free at 3 to 4.
Sir, on Friday we have like 12 to 2, sir, but it's lunchtime.
Okay. It's lunchtime. Let me check if I am having anything there. Yeah, I can accommodate at 12 to 2. Okay, I'm free at 12 to 1. Okay, then let us take 12 to 1 on Friday, because there are a lot more to discuss, but we have less time. I don't want to just skip the topics. I want to discuss it in detail. That's the reason why I'm thinking so. Uh, okay, let us take Friday 12 to 1 class, which I am free. So I can have lunch before that, so that immediately followed by a coding class is there. And on Thursday, let us take it from what is that we have discussed on the time?
1 to 2.
1 to 2. Okay. So 1 to 2 on Thursday, 12 to 1 on Friday. So this is what we have decided. And please remind me at the time, because I don't have in the timetable, so I generally forget if possible. So please remind me at the time. And if there is any work or urgent work I had, I will just remind you that I can postpone the class. So next week also we can take it. But before finishing up with the unit test, I want to finish a max of this one and discussion. So I will also discuss about how to write a code on what we say the deleting the node if you are unable to try it out. So what I will do is, after trying it out, you will also follow this assignment with me. So I will give an assignment. I will also prepare assignments in this week. So the basic assignments I will give, and next week I will give little bit complicated assignment. So in the basic assignment, you will also delete the node and all. So this is how you will do it. Okay. So let us today go with heap trees.
Excuse me, sir.
Yes, Arun, tell me.
Sir, there is an assignment already in the Moodle, sir. Can you just explain that?
Hmm. Which assignment is there in the Moodle?
So something like demo tests, sir.
Demo.
Uh, Demo tests, sir.
No, don't attempt that. I will anyway delete that one. That's only for explaining other faculty of our department how I am doing with code check. I have just yesterday took a small demo class for them. That's all. That's
Okay.
not for you. Okay. Okay. Let's go for heap trees. Heap is generally called a priority queue also. So why I have skipped the priority, now you will understand. So we had a priority queue concept in the previous stacks and queues, right? But I have skipped it. The reason is most of the priority queues are implemented as heap. So heap is also implemented as complete binary tree. So you can say that it is almost complete binary tree. So can anybody tell me what is a complete binary tree? I will draw some diagrams for you. You decide what is a complete binary tree. Which one of these is a complete binary tree?
The second one, sir.
Second one. Yes. So this is wrong, and we get this second one correct. Okay. The second one is the complete binary tree. What is the principle of a complete binary tree?
Sir, in complete binary, we have to first put them in left order. First fill in the left, then go to right.
Yes, that's correct. So the principle of complete binary tree is we fill the leftmost position first. We fill the leftmost position first. So this is important thing. So why I have skipped the implementation of the complete binary tree is due to this reason. Because we now implement priority queues and also complete binary tree in a single concept called heap tree. Now you remember this one, that's all. So in the next slide, I will explain you on how to construct a heap tree and how many types of heap tree are there. Let us look into the types of heap tree. Excuse me, just a second. Okay. So types of heap tree. So there are two types. One is min heap, the other one is max heap. So one is min heap, the other one is max heap. So what is min heap? Generally, when we construct a tree, because we have this as complete binary tree, I have to write it like this. This is a complete binary tree, right? Now, if I put the nodes into it, let me write down like this. If I write something 50, and we have 25, and we have 30, we have 10, and we have 12. So this tree is called max heap. So remember, heap is nothing but implemented as binary heap. Why we call binary heap? The reason is that in a heap tree, you have one root node and a left right nodes. You have one root node and left right nodes. So this is the reason we already discussed, either it should have 0 children, 1 child, or 2 children. It's max. So heaps are generally implemented as binary heap, and they are also sometimes called priority queues because you implement a priority queue using heap with much easiness when compared to just using arrays. It is very good that if you can use heap tree, your priority queue is much easier when compared to arrays. So remember these points. Heaps are generally implemented as binary heap is the first point. Okay. The next point is that heaps generally are also called priority queues, or priority queue is generally called as heap. Okay. And heaps are divided into two types: minimum heap, maximum heap. Generally remember, when the processes are going into the processor, so why we are learning all these things? Because there is some real-time implementation of this. When you study operating system, you will also know about priority based processing. So for example, I am printing something and I am running a small program. I can give priority to these. So if even the printing comes first and the program comes next, the first process to be executed is the program, because I am giving the priority. Maybe I can write down like this. So I will say printing is having a priority 2, executing a program is having a priority 1. So even printing is a process that comes first in the queue, okay, with friend here. And this is rare where executing program will be there. In priority queues, with priority execution program will be executed first because we exchange them, we swap them, and we sort them. And finally, this priority should be coming to the front in such a way that it looks like this, and this shall be executed, and then only printing will be executed. So this is generally studied in your operating systems. So this is the most real-time implementation of the trees also. Not only this can be implemented in processing the databases to find out the data and all. So that is the reason why you study the basics of heap tree. So you have minimum and maximum heap tree, and why this tree is called maximum heap. All the parent nodes are having maximum value when you consider the child nodes. So these are child nodes, right? This is the parent node 50. In this case, this one is the parent node and these are the child nodes. When this case is done, this is called parent node and this is called child nodes. And for child nodes 10 and 12, you can see that 25 is having higher priority. And it is also the parent. 25 and 30, when considering 25 and 30, the 50 is the parent. So 50 is greater than 25 and 30. And hence, all maximum numbers are placed above the smaller numbers. So this is a max heap. Now I can write down something like 5, 10, 15, 25, 30, 60. And this can be called as minimum heap. I think by this time you understand that if you consider this one as parent, these are child, the children are higher than the parent and parent is minimum when considering the children. So you have the minimum values set first over the maximum values. You see on 25, 30, 60, 10 and 15 are placed. On 10 and 15 your 5 is placed. So the entire minimum tree will be starting with a smaller number and the leaf nodes will have the largest numbers. The entire max heap will have starting as the maximum number and the leaf nodes will have the least numbers. That means the minimum numbers that are there in the tree. So this is max heap and minimum heap. So I hope you understand until now. Now my question is, how do you construct a complete binary tree which should be your heap tree? Forget about these things. First of all, if for example I am giving some 5 as a number first, which is considered as a root, and the next number should be placed to the left side of 5, maybe some other number 10, and the next number should be placed to the next of 5, that is right side, because after leftmost is filled we are going to the right side. Maybe this time I am filling 1. Forget about the arrangement. First of all, your mind should think about how can I place this on the left side. The next one is 20. Then we have to fill something like 2. Then we have to fill something like 6 and so on. This is what you have to think in your mind. If you keep that thinking in reserve position, like how I can construct a complete binary tree to form a heap. Let us now construct a heap tree that is called minimum heap. So let us look into this. The first node I want to insert is 50. Now you should tell me at every position whether it is satisfying or not. Because this is the first node, I want to keep it as a root. Okay? There is nothing that single root is there and nothing to compare. Fine. Next, I want to put 10. So according to the complete binary tree, at what position I have to keep, left or right?
Left, sir.
Left, sir.
Sir,
Left. Okay. I will come to left here. Now, is it satisfying the minimum heap? I want to construct
No, sir.
minimum heap. Is it satisfying minimum heap?
No, sir.
No, sir.
No. So according to minimum heap, the parent should be having the minimum number and the child should be having maximum number. So who is the parent of 10?
50, sir.
50. So now you compare 50 and 10 and exchange the values. So the values will be 10 and 50. That means you are swapping it, 10 and 50. The next number that you want to insert is 5. Where I need to insert 5 first, according to complete binary tree.
Right of 10.
Yes, on the right of 10, 5. Now we have a child here. Compare it with the parent. What should I do? Shall I swap or keep it like this? Is it satisfying the minimum heap?
Swap, sir.
Swap. So when you swap these two things, you will have 5 and 10. Okay. The next one, I want to insert 100. Where do I insert 100 now? According to
Left of
complete binary
50.
tree. Left of 50, right? 100. Is there anything that I need to swap, or is it satisfying the minimum heap?
It is satisfying, sir.
Satisfying, sir.
Satisfying the minimum heap. Now I want to insert 1. Where should I insert 1 first? According to complete
Right
binary,
of 15.
right of 50. So this forms a complete binary tree first. But this is not satisfying minimum heap. So what should I do? This is our child now. Who is the parent of 1?
50, sir.
50.
50. What shall I do now?
Swap.
Swap with
Swap.
50.
Swap them. Swap both of them in such a way that I will have 1 here and 50 here. Now you are here. And who is the parent of 1?
5, sir.
5, sir.
5.
5. So according to this, it is not about the value. You are exchanging in the same address. For example, the address is maybe we will go with the addresses like 0, 1, 2, 3, 4. So the node will be 1 itself. You are only in exchanging the values, that's all. And the node will be 4 itself. You are just changing the values 1 and 4. And because now we are at 1 and 1's parent is 0, right? And hence you will consider swapping it. Only think about each node as 0, 1, 2. This is another representation of a heap tree. The first root node is 0. In the next level, the two things are 1 and 2. In the next level, how many numbers will be there? Can you tell me? 3, 4,
4.
5 and 6. So 3, 4, 5 and 6 will be there in the next line. In the next line, 7, 8, 9, 10, 11, 12, 13, 14 will be there. So like that you think about the addresses. And by this time you might observe that because 0, 1, 2, 3, 4 are there, they look like indexes of an array. So keep something in your mind, get an idea immediately. To save some space, I will just 150, right? So I will expand like this. I will drag it to other levels. So what are the numbers that we got? Do you remember? What is on the right side? 5. And then 100.
150, sir, next.
Yeah, this is 50.
And 10, sir.
This one 10, right?
10, sir.
Yeah, that's all. Okay. So all the numbers have been accommodated. So here we form something like, I will write it like 0, 1, 2, 3, 4. So this is how I have written. Now I want to keep some other number. 2. Where should the 2 be? Where should I
Left
place?
of 10, sir.
Left of 10, because to form a complete binary tree, the 2 should be placed here. Okay, now this is the child. So I am telling you how you are constructing it. Once you place it to the left side, now you tell me how you construct this one, heap. So this is the child now. Who is the parent of this child?
10, sir.
10. So you need to exchange both, because to satisfy the minimum tree. This is 10. And again check out. Now this is the child, and what is the parent of this child?
1, sir.
1. So there is no need for you to exchange. That's all. Okay, it's satisfying the minimum heap. Now I want to put something like Okay, some other number we will put 30. So naturally 30 should be placed here. So no problem for 30, no exchanges. But still we have to compare. How we can say no problem? Because computer is blind. By seeing this, I can say okay, 30 is at the correct position. I don't need to compare. But here in computer, it will compare these two. Who is the parent of 32? So because it is minimum, there is no exchange. You stop there. The next thing is I want to put 4. Where should I put 4 actually?
Sir, actually to left of 100, sir.
Yes, to the left of 100, I need to put 4. And what is the number that we are giving for this is 7. And now, is it
Parent of 4 is 100.
yes, to satisfy minimum heap, what is the parent of this child?
100, sir.
100. So naturally, you will swap it. So 100 will be there and 4 will be here. And again, because swapping is done, again you have to check with the above one. What is the
5, sir. Parent of 4
5?
is 5.
Should we need to exchange?
Yes, sir. To satisfy minimum heap.
Yes. So to satisfy minimum heap, we need to exchange it. And I think this until now this is forming the minimum heap, right? This is
Yes,
forming
sir.
the minimum heap. Now, for example, if you have something like this, an array, you are having a list, a dynamic list. Okay, you are slowly adding one by one. So the first number that you have added, the second number that you have added, let me write down a small array for you. So now you know how you can write down a heap on your paper, like exchanging, how you can construct a heap. Now let us discuss on how the computer might think about this heap tree. I think it is enough. Let me write down the values like 0, 1, 2, 3, 4, 5, 6, 7. Sometimes you might wonder, sir, do we really need to construct a tree, or just we can write down an array? That's your wish how you construct a tree. Do you want to keep the addresses in the array, or do you want to keep the values in the array? Let us first look into the value type. So what I will do now is I will take these values. What is there in 0? Can you tell me?
1, sir.
Yes, 1. Next,
2, sir. No, 4, 4, 4, sir.
4. Next,
2, sir.
2. Next,
5, sir.
5,
50, sir.
50,
10, sir.
10,
30, sir.
30,
100,
100.
sir.
Now if you got this array, I want you to find out, for example, we are at 7. Find out the parent of 100 at index 7. How do you find out the parent of index 7? So, for example, in our diagrammatic representation, we can see that the parent of 7 is 3. The parent of 7 is 3, right? It's easy that we can find out. And the parent of 4 is 1. And parent of 3 is also 1. Now, can you write down any formula to find out whether 100 can be swapped with its parent or not? First of all, you need to find out the parent itself. How do you find out the parent? That's important here. Any idea? I'll give you 5 minutes of time. Just think about how can you get this number. Don't look into the internets.
Sir, maybe 7 divided by 2. Like
7. Okay, let me check out. 7 divided by
So 2 divided by 2 fractions 2, like which gives integer, sir.
tell me as a whole.
7 divided by 2, like 2 slashes, double
Okay,
slash
2 slashes.
2,
So what is the answer that you will get?
3, sir.
3. Okay. So if you apply the same thing for 4, 4 divided by 2 will give you 2. Right? That means your formula is wrong.
So in case of even numbers, you can subtract 1 then.
Okay, we can subtract 1, right? Hmm. So let us check out for all. For 7 we got. Let us check out for 8. It will give you
3, sir. 4 minus 1, 3.
because 4 minus 1 will be 3. Yes, 3 is the parent for 8. For 9 we will check out. 9 divided by 2. What is
4.
9? It will also be, because it is divided, we get 4. That's all right.
Yes, sir.
Yes, sir.
Yeah, 4. And because it's an even number, we can say that it can be there. So even or odd. But I think finding even or odd is little bit again taking some time complexity. Saurit, I hope so. You understand.
Yes,
You see, doing minus 1 means again you need something like, why can't we use a single formula without any conditional statements? So if the index is even, do minus 1. If the index is odd, don't do anything. This takes some conditional statement. Why can't we remove these conditional statements and put down a formula directly? So it is correct, Saurit, but still it is not efficient. I want the more efficient one. Come down with mathematical formulas which will eliminate the conditional statements and improve the efficiency of your code. Shall I give you 1 or 2 minutes, a couple of minutes, or shall I tell it?
No, sir, just give us 2 minutes.
Okay, fine. Continue.
Sir, can you just, I'm telling the equation, can you just write it on the board?
Yes, I will.
Sir, n
Let
2
me know.
slashes 2. Yes.
Okay. Yes, tell me.
So just like I don't know it's correct or not. Like n double slash 2.
10
N,
n
sir. N, sir. N for
okay.
nest. Yes, sir.
N
Yep. Double slash 2
slash 2
minus
minus,
parenthesis open, sir.
okay,
N double slash 2
again
again.
double slash 2,
Parenthesis close, sir.
uh,
Percentile 2, sir.
percentile
2, sir.
2. Hmm. So let us check for 10. So 10 divided by 2 means it will give you 5 minus 5 divided by 2, right? So 5 divided by 2 means what will be the percentile answer that we will get?
1, sir.
Yes, 1. So 5 minus 1, 4. 8, 9, 10. That's correct. Okay, that's also good. And any other thing that we can get like 10, 11, 12. Okay, let me say 13. Okay, so give me the answer for 13. 13 divided by 2. I'll rub up this one. Okay. So we will have 13 divided by 2. What will be the answer for that?
6, sir.
6. 6, 12, and we do only division, and it gives us 0, right? So 6 minus 0 will give you 6. Okay, fine. It's going
Sir,
on.
there can be one more.
Yeah, you can.
Sir, n minus 1, with parentheses open.
N minus 1.
In that they are considered as one unit, and then double slash 2.
Okay. Double slash
2.
2. Okay. So let us write something like 13 itself. So 13 minus 1 will be 12. 12 by 2, 6. So we have 13, 14, 15. Let us consider 15. So 15 minus 1 will be 14. Yeah, 14 by 2, 7. This is also fine, I hope. Tell me any other index. Let us see whether we will get it or not. 10, 11, 12, 13, 14, 15, 16, 17, 18. 9. So for 17 and 18, the 9 will be the answer, I think. So let us take 17. So 17, no. So what is the parent of 17? Can anybody tell me? Just write down on paper and tell me. 8, 9, 10, 11, 12, 13. Yes, it is
8 is
8,
the
right?
parent. 8,
8,
sir.
8. So 17 minus 1, 16 by 2, 8. Fine, that's also fine. 18. For 19, the answer will be 9, I think. So 19 minus 1, 18. Okay. For 20, 20 minus 1, 19. Now consider 20. So 17, 18 will be 8 and 19, 20 will be 9, right? So 20 minus 1 is 19 divided by 2. What is 19 divided by 2?
9,
It
sir.
also gives you 8. 8
9.
only, no? 9, 9, 9. Yeah, 9. Okay, that's fine. Who told this?
Sir, Mehak.
Mahak. Okay, very good, Mahak. I could not hear you. Fine, fine. That's good. So I think Saurit, it's more eligible thing when considering yours, I
Yes, sir.
think. Yes. So we will rub this
Yes,
part.
it's simplified, sir.
Yeah, it's simply simplified without any further operations. Because on mathematical formula, your time complexity for both of you will be same, but still processing power is little bit efficient in this case. Okay, that's good. I have another formula for this. I can also go for like this, a seal of n by 2 minus 1. Of course, it's the standard formula. So I don't want to tell the standard formula. I thought like how the students can get it. So most probably they look the same. The seal means you have to use math library, and in the you have to use seal of n divided by 2 minus 1, and initially you have to use math dot seal of n by 2 minus 1. This generally gives you the formula, the parent of a particular node. Okay. Now, so we will go with this formula. Okay. So don't use seal also. Use this formula what Mehak has told. Good, Mehak. Thank you for both Saurit, Mehak, and others who have participated. So now I will add another one called maybe this time 2 is added 3. 3. That's correct. So 3 will give us a nice one. Copy, paste, and let's write the next thing that you are adding is 3, right? You can take a list and it's dynamic. In C, it's very difficult, creating a dynamic array. And if you create a fixed array, it will be waste of time. So in Python list, it is a dynamic one. So we are very happy about that. So we have created 3 here. So where should I keep 3 in the tree? Tell me.
Right of 5, sir.
Yes, right of 5. And this is 3. Now the exchange things will go on. Now this is 8. Now find out according to the formula which is suggested by your friend, n by 2, n minus 1 divided by 2. What is the parent of 3 in
1, sir.
index 8? Yes?
Yes, sir, it's 1, sir.
Parent of 3, 3. Sorry, parent of 3 means you have to consider 8, right? 8. 8 as the index. So for index 8, what is the parent index? Let us apply the same formula. By 2. 8 minus 1 is 7 by 2. So what
3,
is
sir.
7 by 2? 3. Okay, so 3 will be there. So now compare the 3's value and 8 value. Now tell me, should I swap these two?
Yes, sir.
Yes, sir.
Yes. Rub off these two. Put 3 here. So slowly we are conquering towards how the computer will understand. And 5 here. So we exchanged. And in our pictorial representation also we will exchange that. 3 and 5. Next, again repeat the process because swapping has been done. Now your process should repeat. And now you are here.
Sir, 3
Now,
minus 2 is 1, sir. Sir,
yeah,
3 minus 2 is 2. 2 doubles 2, less it's 1, sir.
yes. So this will be 1. So according to the formula, we got 1. So now check out 1 and 3. So can we swap?
Yes,
Sir.
sir.
Yes, we have to swap it. So according to this, we can swap. So this will become 3 and this will become 4. In our pictorial representation also, we do the same thing. This will be, sorry, 3 and this will be 4. Again, swapping has occurred. So I think now you have to find out the parent of 1. So 1 minus 1, 0 divided by 2, it will be 0 only. So can I swap 1 and
No,
0
sir.
here?
No, sir.
No, you keep it like that because there is no swapping happened, there is no further recursion to take place. Or even if the swapping happens also at 0th position, there is no further recursion, you can stop there. So recursion can be stopped in 2 ways. If you reach 0 or you have stopped swapping, that's all. So I think now by this time it is fulfilling the idea of minimum heap. So I think now you understand this. Let us now try out 0. 0 as the value itself. Okay, so 0 should be going from here to here all this way. Okay, so now consider 0. So 0 will be at the 9th position. So I will create another list like this. And this time you will have 9 and 0. Now tell me based on the formulas, what is the parent of 9? 9 minus 1, 8 divided by 2, 4. So
You
can we
should.
exchange 4 and 9?
Yes, sir.
Yes, sir.
Yes, we can exchange. So I exchanged 4 and 9 and 50 comes here. Here also 50 comes here and this will become 0.
Sir,
Okay?
next one is 1, sir. 4 minus
Yes.
1 is 3. 3 by 2 is 1.
3 by 2 is 1. So you also
You can
need to
swap, sir.
exchange. So what are the things? 4 and, so this is 0, right? Okay, I'm sorry. This is 0. So 4 and 1 should be exchanged. So it becomes 0 and this becomes 3. Okay?
Yes,
So
sir.
this becomes 0 and this becomes 3. Again, swapping has occurred and verify. 0 and 1. What shall we do?
Sure, sir.
Exchange again. Okay, 0 1. Here also we need to exchange 0 1. So I think you can use this tree as a pictorial representation, but you can put the nodes in an array or a list like this, like your queue, and swap the nodes. That will be fine, right? So your entire tree will be finished immediately. I hope you can understand that. So there are different types of implementation. I got some idea, you get some idea, and we will discuss about that in the next class. Okay. So I will do something like I will include all the nodes in the queue and I will do the insertion. maybe I can use this list also. You do it in this easy way or something else. We will all discuss our implementations. Okay, so we will stop the class now. Bye bye.